So there are no matrices questions from 2022 or 3 from step 3, but there was one in 2024. It was this one. Let's go ahead and do it. So we've got matrices M and N that are non-singular, blah, blah. The trace is defined. We've seen trace before in some other step questions about matrices. Prove this thing first, and then let's think this. This is not too difficult, right? So we could say M and N are these two things, just using all the letters that we know. And then, of course, M times N we could work out is this thing. I didn't even bother to work out these because the trace is just these, the leading diagonal added together. I wouldn't suggest that you be list lazy when you do it yourself, but I was really lazy. And then, of course, you can multiply them the other way around, which, of course, for matrices is different. But whatever happens when you do the trace, of course, the trace is going to be the same thing, just because the only two terms that have swapped are these two, and everything else is the same. So we end up with the traces are equal. And then we can do for m plus n, which is obviously this. The trace is just these two things added together. And of course, A and D is the trace of n, and E and H are the trace of n. So this is just the trace of m plus the trace of n. Okay, so that's just the stem essentially done, I think. And then it says we've got the entries in M are not just constants, but they're functions of t. And dm by dt is just when you differentiate each term individually in the matrix. Show this thing here. So the left-hand side, well, 1 over m is AD minus BC, as we know. Oh, sorry, 1 over determinant of n, so that's there. And then the determinant of n, as I just said, is AD minus BC. If we differentiate that, we can use product rule to differentiate this because it's A times D, right? And they're both functions of t. So it's A dash t, D plus D dash A. Something like that. Same thing down here. And I'm just going to leave that where it is because now we can work on the right-hand side a little bit. We can say the right-hand side is this thing here. M inverse is just, of course, 1 over AD minus BC, and then you swap these two over and then make these two minus. And dm by dt, as we said, is just the derivative of every term in here. I'm using dash to represent the derivative. I hope that's okay. And then we multiply out this matrix here. And then when we take the trace of this, of course, all this constant here does is just lower every term or divide every term by this amount. So, of course, we can just put that in there, and then the trace will be this divided by this minus this divided by this. But we can, of course, just ignore the divided by and bring it out again, and we end up with the exact same thing that we had in the right-hand side. So therefore, the two things are the same, and I think that shows that result just about. Okay, now we have a differential equation that's part of it with matrices, which I've never solved before or thought about before, so that's quite cool. Show these things here. Now, okay, well, if we're thinking about I mean, you can see I've got all of my results up here um, that we've done so far. They wouldn't ask you to prove this result unless they intended for you to use it. Now, the only thing that we know about m, really, I mean, it's still a, b, c, d as it was before, I guess, as functions of t. But the only thing we really know about it is this thing here. Now, we look across our results that we know, and we can see dm by dt is in this result here. So let's just take this right-hand side and take the trace of m inverse times dm by dt. But we know dm by dt is m in n minus mn. I should have had another closed bracket here. There should be one more bracket there, but that's okay. Now, of course, we can multiply this out to make this, because of course m inverse times m is just the identity matrix that makes an n, and then here we get m inverse n m. But that's okay because now we can use this result for a trace to show that this is trace n minus trace of this matrix. But now if you think about n m, that's just a single matrix, right? It's a 2 by 2 times a 2 by 2. It's some other 2 by 2 matrix. So think about that as a matrix on its own, and then apply this result where we can just swap the two matrices over. But now, of course, m times m inverse is just the identity, and this is the trace of n, which is 0. So now that we know the trace of this is 0, that means, I think, that if we were to derive, well, that means that this is 0, I guess. Sorry, that means that this is 0. Now, 1 over det m can't really be 0. So that means that d by dt of the determinant is 0, which means that the determinant is some kind of constant. Because when you derive it, you get 0. So therefore, it's independent of t. Like if it had any t's in it, when you derive, it wouldn't always be 0, right? So it must be some kind of constant. We're going to use similar ideas to get these two results here, where we're going to think about the fact that we could show that these are independent of t if we just show that they're constants, and therefore that they derive to make 0. So let's think about the derivative of the trace of m. So of course, well, the trace of m we can say is just the two leading diagonals added together. But of course, if we derive those, we'll just derive the two terms separately. So therefore, we may as well derive the two terms first and then add them together, right? It doesn't matter if you derive or add because they're independent of each other, I guess. So this is essentially saying a plus d derived is a dashed plus d dashed, but this here is a dashed plus this is a sorry, this is a dashed b dashed c dashed d dashed, and when you take the trace, it's a dashed plus d dashed, so it's the same thing. So that's okay. And now we can think about the fact that, of course, based on, again, this differential equation, the only thing we know about dm by dt, we can shove this result into here. And now we can use the results that we know about trace functions, which is what we can take them away separately. And then, of course, this is the same as when we swap them over. So we're taking away the same thing from itself, so it's zero. So therefore, the derivative of the trace is zero, which means the trace is some kind of constant or independent of t, the same thing we said before. And now the trace of m squared, probably the most tricky one to think about. But we can work out m squared, right? It's just this times this, where these are all functions of t. We can multiply those together. Again, I don't really care about the diagonal ones. They're just some other functions of a, b, and c, and d, which are functions of t, I guess. And then we can add these two things together to get the trace, which is this. Now, how do we show that that's essentially independent of t? Well, we can use the previous things that we've just found. We know the determinant of m is independent of t, and we know the trace of m is independent of t. Is there some way to hammer those results into here and make this some kind of combination of the two that we just found? Well, we can say, of course, the trace, remember, is a plus d. So we're thinking about getting an a plus d term in here. Now we can get an a plus d squared term in here as long as we get rid of a cross term. So that seems decent. And the determinant is bc minus ad, or ad minus bc, really, but it doesn't really matter which way you write it because it could just be a minus. And that's perfect because both require getting an ad term in there. So we can add two of them in just to take it away. And then these three terms are a plus d squared, and those two terms are minus the determinant, or minus two lots of the determinant. And since both of those two things are independent of t, when you combine them together in some linear fashion, you also make something independent of t. So therefore, we can argue that. Okay, so now we have in the specific case this, where these are all functions of t, find m as a function of t. So let's just, I mean, we know m obeys this thing here, so let's just do it. Let's call all of these functions derived a dash, b dash, c dash, and d dash, and then just put in all of this stuff into here. And let's do a little bit of calculation here. It's not too hard, it's just multiplying matrices and simplifying, and we get to this. And now we can see for these things to be equal that c dashed must be zero, which means c is some kind of constant, so we can just call it maybe little c, which would then make a dashed equal to minus little ct, which of course we can now just integrate both sides, right? Because we just got dA by dt equals minus ct, just integrate both sides, and maybe call your constant k1, obviously not c because we've already used it, and then I'm going to have more constants coming, so I thought I'd just call it k1. I can do the same thing, of course, with d dashed, which is ct, integrate both sides, call it some other constant. And then finally, b dashed is this, but I know a and d now in terms of t, so I can just put those results in, which makes this, when you times them by t, you end up with this. And then, of course, you can just integrate everything. I've also grouped together these two terms, and you can, of course, group together those two terms and now integrate everything, and you end up with this here, which we can then just put all those functions into a matrix, and we end up with this thing, roughly something like that there. Now it says we have this different differential equation, dm by dt equals mn, and apparently the trace of m is non-zero and independent of t, so it must be something like 4. Yeah, it's just got to be some constant that's not zero. Isn't necessarily true that the trace of n is zero. So, I mean, if you're doing step, you've probably taken the Tamura. Is it necessarily true? The way that we would solve this if we were doing a Tamura paper was just to find a counterexample where it's not happening, and then we can just say no. So can we find a counterexample? The good news is that this is a relatively simple differential equation, so it doesn't seem like it's going to be that hard, although it is, to find, or at least I found it, to find an example of a matrix M and N that do this. The first thing you think when you look at this is, well, if these weren't matrices, this is just the derivative of M being some constant times M. And like we know what the solution to this kind of thing is. It's when x is e to the kt, right, which differentiates to itself with a constant in the front. So maybe we should try matrices that have this idea in them, so that when we derive, we just end up with a constant times it, right? Maybe that's a good start. Now we need the trace to be non-zero. So these two numbers seem like decent ones to go for on this diagonal because the e to the t's cancel and you just end up with a 1 here. So okay, well I tried this first. Differentiator, of course, is this. And so now can we think of a matrix n in terms of t that would times by this to make this derivative? Because that's what we want to make, right? So okay, well this expands out to this, and then we see some problems pretty quickly. C and D look like to try and make this thing match this thing. C and D are basically going to have to be 0, right? But of course up here, A and C need to add to make 1 when you factorize out the U T, and so do B and D. But if C is 0 from here and D is 0, then A is a half and B is a half. It just doesn't make any sense. Like, it doesn't work. These constants kind of just mess you up. Now, C and D are not necessarily constants, right? They can be functions of, or they are functions of t themselves. So it's worth thinking about the fact that you could try and make C like e to the minus t here. And we'll actually have to try that tactic in a second, I think. Because like e to the minus t would cancel this down to a 1, which you could then maybe use the other functions in terms of t to cancel them out again. But here it's still not really going to work because this top row just doesn't have any of that in it. So the moment you try and make that an e to the minus t, it just messes up your top row instead. So the way to try and make this a little bit better is to try and give yourself these terms in the top rows, or even though these terms are the problematic ones, try and put those in the top as well. So if I put a 1 here as well, then I can get some more of those terms up in the top, and I might have slightly more of a chance of making this work. Now we can see that these two terms should be the same, which is basically going to have to give us, and likewise, these two terms basically need to be the same down to a minus. So, well, that's sort of okay. That kind of leads C to be 0 and D to be 0 straight away, which nearly works, I guess. It doesn't really work though, because then, of course, this term doesn't work when you need a. No, that term does work, which is the one that doesn't really work at all. B needs to be a -1, but it needs to be a +1 here. So it's actually much closer, but it still doesn't work. Again, think about using e to the minus t instead, because then this term could be a 1, but then you start messing around with here. You could think about, again, being another e to the minus t to try, or a minus e to the minus t to try and cancel this out again. But it's still, if you follow through, doesn't really work all the way around. But maybe this gives you the idea that you should be trying to put in this minus t, which rescues the situation when it starts canceling with things. Maybe you should just put this in here instead, right? And give yourself it straight away. So what if we try that there? Then does this work? Well, we differentiate to make these things here. And now we can argue that, well, okay, looking at these two terms, these should apparently be the same. So c equals 0 is pretty much, maybe it doesn't have to happen, but it would be an obvious way of making this work, and a equals 1. And then looking over here, well, again, these two things don't have to be the same anymore, which is great. It looks like we need the d to be the 1 because it gives us this e to the minus t. But if we use d as 1, then we get a 1 here, which means b needs to clear that 1 out, which it looks like it will if we use an e to the minus t, or even more specifically, a minus e to the minus t, which would give us a -1 term there, cancels. This is good. A minus e to the minus t would give us a -1 here, cancels, and then good. So that seems like it actually works, and we found our counterexample. Horrendous thing to find. It was only worth 3 marks for that entire last section. But long story short, the trace of n is 2 here, and the answer is no, it doesn't have to be. Yeah, really hard to find. Maybe there are other kinds of examples. I, of course, had the advantage of able to look in the mark scheme and be able to find what I was supposed to be looking for, which allowed me to reverse engineer the steps to kind of logically get there. But if you're doing it completely blind, it's obviously even harder. It was only 3 marks though, so yeah, maybe it's not too big of a deal. But I thought it was a really tough ending of that question. Anyway, thanks for watching.